I'm going to introduce you to the phenomenon known as relativity of simultaneity. And this is a phenomenon that Einstein figured out by deriving it from the two principles of special theory of relativity, which state that the laws of physics are the same in every inertial reference system, and also states that the speed of light is always measured to be the same speed relative to every inertial reference system, no matter the speed of the observer or the speed of the source of the light. So just using those two principles, you can derive the phenomenon known as relativity of simultaneity, which really is just a phenomenon of which, let's say you have two events that happen at the same time from one reference system. It's the relativity of simultaneity says that from another reference system or for any or every other reference system, it cannot always be stated that those two events happen simultaneously relative to those reference systems. Now, it might happen simultaneously relative to one reference system, but not every or any other reference system. And it really has to do with deriving from those first two principles and moving. So whenever you move relative to an initial reference system, that's what happens. Where some other reference systems, specifically the moving reference system, does not have the same two events happen simultaneously from their reference system, versus the reference system that may be at rest does have two events happen simultaneously. So simultaneity isn't the same from every reference system. Two things don't always happen simultaneously from every reference system whenever it happens simultaneously in one reference system. So to understand why, we're going to start off with really measuring how can we tell whether two events happen simultaneously from one reference system? How can we tell that? So let's say we have one reference system and we see two events. If we can prove that they happen simultaneously in this reference system, if we start off with that and we get another reference system and we move it, if we use those same rules for the first reference system, if we use those rules for the second reference system that's moving, and we find that whenever the two events that happen, we find that they just don't happen simultaneously. Relative, using the same rules from the first reference system. If those same rules can be applied to the second reference system from the first reference system, then in the situation in the second reference system aren't really obeying those rules, then it can be stated that the two events in the second reference system do not happen simultaneously. So let's see, how can we figure out whether two events that happen in one reference system simultaneously, how can we tell they do? So let's say you have somebody standing right here. Let's say it's you. You're standing right here. Let's say you have two paint cans. And let's say they're at the same exact place and at the same distance from you. So let's say they explode. Let's say this can explodes and this can explodes. So we know they're the same distance from you. If we can measure them to happen at the same exact time, if we can, what I mean is, if we can measure the time that the light from these two exploding cans to reach you, if we measure them to reach you at the same time, then we can justifiably say that these two cans exploded at the same time, because they're the same distance and the time that it took the light to reach you was the same time. So now this is just measuring to see whether two events that are in the same place in one reference system happen at the same time. Now, let's say there's two cans that are separated spatially and they're equal distances from you. And let's say they explode. This one explodes and this one explodes. So they're equal distances from you. If you measure the light from these two exploding cans, the moment they explode, to reach you in the same amount of time, if they reach you at the same time, then you can justifiably conclude that they exploded at the same time. Now, let's try and apply these same sort of rules to another reference system that's moving. So let's say there's a van. You're still standing right here at rest, and you're in an inertial reference system, and the van is right here moving forward in this direction relative to you with the constant velocity. Therefore, it's also an inertial reference system, and Newton's laws of motion are valid in both of these inertial reference systems. Now let's say your friend is in the middle of the van, and let's say there's a can in the back, and let's say there's a can in the front. Now, Let's start off by saying that the speed of light isn't the same for every inertial reference system. Let's say that the speed of light, whenever it leaves this back can, let's say the can explodes in the back, and the light leaving, the moment that the light leaving from the can, the moment it exploded, it left from this position right here. And it's leaving at the speed of the van plus the speed of light, which is about 3 times 10 to the 8 meters per second. So it's going to be the speed of light plus the speed of the van is going to be the speed of the light moving from this exploding can at the moment it exploded, from this position. And the person, your friend in the middle of the van, is going to be moving this way. So it's going to take a longer distance from the light from the exploding can back to reach your friend in the middle of the van. It's going to be a longer distance than the light from the exploding can in the front of the van at the moment it leaves from this position. It's going to take a longer distance right here. This distance is going to be expanding, and this distance is going to be contracting. How can I draw that? Let's see. It's going to be doing something like this. So this distance is going to be increasing, and this distance is going to be decreasing. So let's say the formula for velocity, or the formula for speed, let's say speed is just distance divided by time. So we have speed, let's say this is going to be, we can say this speed right here, the speed for the can in the back, the speed of light for the can in the back, let's say it's 1.5 c. Now let's say the can in the front, the speed of light is going to be 0.5 c. And the formula for that is just going to be distance over time. And let's say this is going to be changing. So we can replace, we're going to switch these right here. We're going to switch the time and the speed for both of these formulas. So we're going to get time is equal to distance divided by 1.5 c, and time is equal to distance divided by 0.5 c. So we know that the distance for the can in the back, let's say if the speed of light is 1.5 times the speed of light for the can in the back is going to be about 1.5 times the speed of light normally, the distance is going to be increasing by a factor of about 1.5. And for the can in the front, the speed of light would be about half the speed of light normally. And the distance in the front, the distance from the person in the middle to the can in the front is going to be decreasing by a factor of about 0.5. So we know that the time that the light's going to take to reach the person in the front is going to be the same for both scenarios. And that's whenever the speed of light is not the same for every inertial reference system. So basically, it's just a little bit different. If you was to measure the same time for the cans that are equal distances for a moving van or a moving object, you can't say they happen simultaneously, I guess you can say, or you might be able to, but it's a little bit different. It's more complicated. But let's say that speed of light is the same for every inertial reference system. So let's say that your friend in the van moving forward, there's a can in the front, there's a can in the back, and let's say, first of all, let's look from your point of view right here. And the van's moving relative to you with a constant velocity, and you're in an inertial reference system right here while you're standing at rest. So whenever you measure the cans to explode, let's say the cans explode, they're equal distances from you, and the time it takes for the light to reach you, let's say they reach you at the same time. So you say the cans explode at the same time. But your friend, however, they're moving. So the speed of light's the same relative to every inertial reference system. The distance relative to this point right here to your friend is increasing, and the distance from the can in the front from this position, the moment that the light leaves the can from whenever it explodes to your friend inside the middle of the van is decreasing. So if you write a formula like that, it would be C is equal to D over T, where the distance in the back would be increasing. Let's say it's 1.5 times, like this. It's increasing distance, and so the time must increase. And let's say for the back, for the can in the front scenario, the time would be decreasing. So it'd be 1.5 the distance, zero point 0.5 the distance, and the time must be 0.5 the distance. The time must be half the time. So, in other words, the time that it takes for the light in the front, the light from the can in the front is going to be half the time, and the time for the can in the back to reach the person in the middle is going to be a longer time, and the distance is going to be longer in the back, and the distance is going to be shorter in the front. But anyway, the distance, and the whole point is that the time is going to be different. The times are different whenever the light from the front of the van, the light from the exploding can in the front, that the time that it reaches the person in the middle is going to be different from the light from the exploding can in the back is going to take to reach the person in the middle. That's going to be different times. But here's the thing. It can be stated that the friend in the middle in the van is actually at rest, and you're moving. You're actually moving. Right here. Right here, you're going to be moving. And the van's at rest. But the person in the van experiences different times for the light to reach. So the cans are at different distance. I mean, the cans are at the same distance for your friend in the van. Your friend in the van is at rest, technically. That's a correct way to look at it. And the time that it took for the light from each exploding can, the one that left the can, is different. So they must have happened at different times. Now you may say this. You may say the van's not moving technically, so the distances that they traveled would be the same distance. So technically it would be the same time for the light to reach. But here's the thing. It can't be both. It can't be that the distance from the person in the van, in the middle of the van, to the cans is the same in either case, and it can't be that the distance from the person in the middle of the van to the cans is different. It can't be that both of those scenarios. That would just violate the law of non-contradiction, the logical law of non-contradiction. It can't be that those two scenarios are the same. And we do know from observation and experiment, it's been proven that the light in the front actually does reach the person in the front, in the middle of the van at a shorter time than the person than the light from the back, from the light from the can in the back of the van to reach the person in the middle. So we must conclude that from the point of view that the person in the van is at rest while you're moving right here, you must accept that they view the light from the can in the front to reach them in the middle of the van before the light from the can in the back of the van to reach them. So which means that the two cans exploded at different times. But from your point of view while you're at rest, the two cans exploded at the same time. So really, the two events are not happening simultaneously from every point of view, from every reference system. So that's basically relativity of simultaneity. And really the payoff that you get from this is that when you're moving with a constant velocity relative to an inertial reference system, two events that happen simultaneously from the at rest system is not going to happen simultaneously from your reference system, in that events in front of you are going to happen before events in the back of you. And that's basically all I have to say about relativity of simultaneity.